talking about semiconductors and then move into diodes. So there, in your textbook, the textbook that you have, there is no separate chapter on semiconductors. This is the material that we skipped at the end of chapter 1. So at the end of chapter 1, there's a few sections on semiconductors that introduce the diode. And then in your textbook, we will go to chapter 3 in your textbook. So the homework that will be assigned will be based on your textbook's chapter 3, right, which is the diodes stuff and some of the sections that in this semiconductor text in chapter 1. Okay? So that's a difference. There's a little bit different. They took this section in chapter 1 and in your textbook and made it a separate chapter here in this edition of the textbook. But the content is the same. Right? So with the semiconductor stuff, it will be just some theoretical understanding that will help us understand how the diode functions and what is a p-n junction, etc., etc. What is intrinsic semiconductor versus a doped semiconductor. So today it's just a friendly discussion here. So it's more of the physics. I mean, I'm not sure if you covered any of this material, electrons and holes in physics and motion of electrons, carriers of charge. Have you covered some of that in physics? 370, you cover holes in electrons and... Okay. And you cover intrinsic semiconductors. Okay. So we will talk about intrinsic and extrinsic or doped semiconductors. Okay. So just before we get started, so a silicon atom, or silicon itself, silicon is probably it's the 8th most common element in the universe. So it's an element that is readily available in the Earth's crust. So I think it makes up 27.7%. I was reading it somewhere else, of the materials on the Earth, in the Earth's crust. Yeah. So it's readily available. So it's a very nice material since it's readily available. People are not going to go to war over it. So that's a good thing. But it's not available in pure form, right? So since it's not available in pure form, then you have to process silicon to be able to utilize it in different applications. So there are many different applications of silicon. Actually, it's used in the construction industry, transportation industry, etc. Many industries, and all of these industries use silicon with different degrees of processing of the material. The photovoltaic industry uses silicon. The electronics industry uses silicon. So the electronics industry happens to be the industry that demands the most out of the purification process of silicon. So it's why is that? Because we depend on creating a pure crystal of silicon that does not react with anything around it. So if when you studied chemistry, and I'm really not a good guy to teach or talk about chemistry, but when you studied chemistry, there were some inert gases. There was some gases that were called inert. Why were these gases called inert gases? What did this mean, or where did this come from? From their electron structure? Do you remember anything from chemistry?
I remember noble gases.
You don't remember noble gases like argon, for example?
Oh yeah, I remember argon.
So why was it called a noble gas?
Because it's not reactive.
Exactly. So it does not react with anything else. And that comes from the fact that it's not reactive means what? It does not form these bonds between it and other atoms. Right? Because its outer shell of electrons is full. Nice. Right? So that's, if you remember some of that stuff, that's the deepest I can go on chemistry, okay? So no, this is really it. So the fact that its outer electron shell is full is the reason why it cannot react with other elements, So silicon is not the same way. So silicon actually has 2 electrons in the first subshell, and then it has 8 electrons in the second subshell, and then it has 4 in the...
Is it 2, 8, 14, right?
It has 14 electrons. So it has 2 in the first subshell. Second subshell has 8 electrons, and then it has 4 electrons in the final in the next subshell, which means it has an additional 4 slots for electrons that it can sort of bring in or react with other elements. So which makes it which makes it a material that is a reactive material by itself. The silicon atom by itself is a reactive, can react with other atoms around it. Yeah. So it just so happens to be, since silicon is a material that since silicon atoms can react with other atoms around it. It happens to be, if we bring more silicon atoms and put them all together and create what we want, and with our goal being to create a single silicon structure, silicon crystal that is very pure, 99.9999% purity, that does not react with other elements. What the silicon atoms tend to do is they come together, so they will react with each other and form covalent bonds. So they will each, fine, I have 4 electrons in my outer shell, you have 4 electrons in your outer shell, and so does 3 other silicon atoms. So we'll come together and we'll fill the outer shell, so that we will share the electrons in the outer shell, so that we can fill the outer shell of all of us with electrons, so that we create a single silicon crystal structure that does not easily react with anything else. Right? So that's sort of where this is headed, yeah. So that's good. Okay. Also, when an electron, so this reaction meaning, so let's assume. So let's assume now. Let's look at the structure of the silicon material. So before we go there, since we said that we want to create electronics from pure silicon, another word for this pure silicon that is used to make electronics, or another word for the electronics made out of such pure silicon, is a monolithic circuit. Monolithic meaning it's fabricated from a single silicon crystal. Okay, so that's another word for integrated circuit. So it's monolithic circuit, integrated circuit. These are such similar some words. These are some words that we will be using here. So if we create this material that does not react with surrounding materials anymore, then all the electrons are intact in the outer shell, and there's no movement of electrons or holes. So electrons are like so it's a negative charge. Negative charge is placed in the outer shell of the atom, and then if an electron is happens to leave that, if an electron in one of these in the outer shell happens to leave the outer shell, it will leave behind what is called a hole, right? And that hole is a positive charge. So so if the electron leaves its position, it will leave behind a hole, right? So in an intrinsic silicon, so intrinsic meaning very pure silicon, single silicon structure, is this going to happen? It will not happen, because all of these atoms are holding tight to each other. So you have all these silicon atoms that have 4 electrons in their outer shell. So what they do is, they team up with everyone around them. So they team up. So this atom here is teaming up with this one, with this one, with this one, and this one, and then they share. So these guys share 1 electron using a covalent bonding process, and then these guys share 1 electron. These guys share 1 electron. These guys share 1 electron. So this is called intrinsic or pure silicon, and these bonds are called covalence bonds, and these are the electrons in the valence shell, or the valence electrons, if you want to call them. This will not react with anybody. These electrons will stay in place because they are in place using this covalent bonding process, right? And that's how you created this nice pure silicon structure that is non-reactive with other materials, right? So that's the pure silicon. Pure silicon by itself, again, since no electrons are going to move, or no holes. If no electrons move, and then there will be no holes available also in surrounding the atoms to also carry charge. The electrons carry a negative charge. The holes carry a positive charge equal to the charge of the electron, right? So if we have, a stream of atoms with, each one with a hole, then I can basically, if I find a way to push these holes to one side, right? If I find a way to extract these holes and allow them to move using some process, which we will talk about, then I will have current flowing. Right? Because the movement of charge, whether it's positive charge, so if you take a piece of semiconductor or a piece of metal or a piece of copper wire, how do you measure current? current flowing through it is the number of charges per unit time, right? So anytime you're able to move charges somehow, then you're able to create current. In pure intrinsic silicon, I cannot move any charge. All of these atoms are bound to each other with covalence bonds. They're sharing these electrons. Nothing's happening. So pure intrinsic silicon is an insulator, basically. It acts as an insulating material.
The covalent bond stops the electron from breaking off.
Yes, unless you're able to break the covalent bond. If you break the covalent bond, and we will see that in intrinsic silicon you can break the covalent bond, but the only way that you can break the covalent bond is using temperature. So it's a thermal process. So if you apply higher temperature to these materials, not I think if you are at 0 Kelvin, yeah, if you're at 0 Kelvin, that's in section 3.1. They tell you if it's at 0 Kelvin, you cannot. I mean, there's this intrinsic silicon will be an insulator, pure insulator, and you cannot do anything to break this bond, right? At a higher temperature, these covalent bonds can be broken by this thermal energy, right? But imagine now I break these bonds by thermal energy. Okay, so let's say I raise the temperature of this device a little bit. So I break the bond and this electron becomes free. What's going to happen in its place? I have a hole, right? And then another electron from somewhere else will become free. It's going to fill this hole. And then this free electron that became free from this one electron that started the process went into and filled this other hole's position, and everybody's back to normal. I'm not moving charge anymore, right? So intrinsic silicon inherently will not be able to conduct current. So it's an insulating material, right? So one of the benefits of or something we should understand. So we said that we're talking about semiconductors. Semiconductors are materials that fall or can be controlled to either look like a conductor or like an insulator, right? So an insulator like glass, for example, is an insulator, or a conductor like copper, for example, is a conductor, right? So semiconductors fall somewhere in between, and semiconductors can be made to behave like a conductor, and then can be made to behave like an insulator, right? How do you make them behave? So obviously now this intrinsic silicon, we realize that it's a non-conductor, it's an insulating material. That I cannot, all these electrons are bound, they cannot move around, so I don't have charge moving in a cross-sectional area, through a cross-sectional area that I can count, right? One is going across this way, the other going across this way, that's it, it's zero.
When you heat the silicon, it becomes conductive.
If you heat the silicon, if you heat intrinsic silicon, then what happens is, okay, all of these atoms, this one loses one electron, right? It's left with a hole. Let's see, so it's left with a hole. But you didn't heat this only single atom, right? You heated the silicon, the bulk silicon material. So it heated the other atom right next to it. So what happened to the other atom next to it? The one electron also became free. The covalent bond broke. Then this one electron kept wandering around, attracted to the hole, and filled the hole again. The other one also nothing happens. There will be a net zero movement of charge.
They have to be like in a place where there's nothing to react to.
Yeah, I mean you created the silicon structure such that it looked like.
I know, but like we have air and dust and all of these things.
Yeah, it will not react like that's why you create this idea of the noble gas. This is not a noble gas, but a noble gas does not react with something else. Why? Because it's full of its electron shells are full. So we created the silicon structure such that we created a material that has electron shells that are full.
That could be manipulated by either adding electrons.
Exactly. So we will have to figure out a way to manipulate the semiconductor material to be able to make it allow it to look like a conductor. Right. So now we said intrinsic silicon is an insulating material. So we want to, but the nice thing about semiconductors, we can manipulate. How can you manipulate? We will talk about that. It's called doping. Yeah. So, not the bad doping, just the good doping stuff. So the semiconductor materials. So there are many different types of semiconductor materials. So there can be single element, or there can be compound elements, materials. Compound element semiconductor materials. So Single element means what? It's made of a single element in the periodic table, like silicon, for example. Silicon is a single element material, like germanium. Germanium is another single element semiconductor material. And so germanium was used for very early transistors. Early transistors we used germanium. Silicon took over just because it's a very abundant material. It has properties that we will talk about later that are interesting for semiconductors. Okay, so silicon took over as we discussed, and then compound elements are obviously semiconductors made of more than one element in the periodic table, right? So one example is gallium arsenide. Gallium arsenide. Another very good example is silicon carbide. These are very hot topics in the power electronics industry.
What's the first one?
Gallium arsenide. Gallium arsenide. So gallium arsenide, GaN switches, and silicon carbide switches. They're pretty much this is the most hot topic in the power electronics business these days. So why? It's because we were able to operate these devices at much higher speeds with a lot less losses, right? And all of this is materials, and this is where the electrical guys and the material science guys interface together. The semiconductor business. Yeah. For me, if I work a lot on the application side of power electronics, right? So our work is quite applied. So we develop controllers for different motors or drives or renewable energy applications, etc., etc. But if you're considering a hot topic, for example, on in power conversion, for example, it's working on materials such as this and how to create power devices with higher voltages and less losses, etc., based on such devices. Yeah. So also compound elements are also used a lot in LED applications. So they are the workhorse of LED industry. So Cree, for example, is one company that started off by making silicon carbide LEDs. Or actually, first they created silicon carbide PN junctions, which is a PN junction is nothing but an LED is nothing but a PN junction actually. So they started creating silicon carbide wafers. So instead of creating a silicon, big silicon, ingot, I think is what it's called, just a big bulk piece of silicon. They create, and then so what we do is, we create these big silicon, pieces of silicon, pure silicon material, and then we chop it up into small, thin wafers, and we build our electronics on top of it, right? That's the process, that's the building of the electronics that we saw in the first video in class. It's built on top of a wafer, so of silicon. So the problem with silicon carbide, the past, people have been spending the last 15 years trying to improve silicon carbide wafers, because you don't want, if you create a silicon carbide material, start chopping it up and start to break, right? Yeah. So if you have cracks, you have failures, etc., then you don't have as many wafers that you thought you had, which means the price has to go up. So when the silicon carbide topic came up, maybe 6-7 years ago, commercially we started having prototype devices from silicon carbide about, I would say, 10 years ago, 12 years ago is when we first started to get prototype devices. A MOSFET, a low voltage, not a low voltage, maybe a 100 volt MOSFET, 200 volt MOSFET was about $250, right? You can buy that for today. It's still not that, it's not cheap, it's not free, but today you can buy a silicon carbide MOSFET maybe for $24, right? So can you see, what happened?
200 volt.
Yeah, from 200 to 20. They were having problems with creating good wafers. So people worked a lot. I mean, for me, this is a huge contribution for research. For the last 10, 15 years, this was one of the major contributions in power conversion research, was the devices that made up of such materials. Yeah. So anyway, and it's the same with LEDs. So LED materials, what?
It's not that old.
No, this stuff is new. This is really new stuff, yeah. And now, after silicon carbide, people started now working on gallium arsenide. So they realized they can push the boundaries even further with gallium arsenide. So today, you cannot really easily buy. Today, the gallium arsenide is where silicon carbide was 12 years ago. So today, you can get gallium arsenide prototype switches.
That's why silicon became cheaper, because they have removed.
Silicon, no, but silicon is cheaper because it's, you know, it's so abundant. It's really
It's
abundant,
insane.
and the processing of it, people have been doing it for years, and yeah, people know how it's done. You can make very perfect wafers with no cracks or faults or things. So when you have an ignite of silicon, you're making use of the whole thing. You're chopping it up into very small wafers, and you're making use of the full
Have
wafer.
you seen the process of, like, when they create the sand to silicon?
No.
Okay. I wanna see how that goes.
I'm sure there are videos online, and my understanding is that the textbook has some links to videos for the process of manufacturing, and the appendix has something like that. So your textbook has an appendix on the manufacturing of PN junction with silicon carbide diodes. You can go to TI. TI in Houston has a big facility that manufactures, you know, electronics in general. So they create their own wafers, they chop it up, and they put devices on it. So TI has a very nice facility in Houston. Very nice facility. My friends used to work there, so I didn't visit though. Or maybe I visited once, I don't remember. So anyway, so we will mainly concentrate on silicon. Here. That's our main emphasis, since, you know, it's still the workhorse of the industry. It is the workhorse of the integrated circuit industry. So all the op amps, etc., you know, most of the transistors that we will deal with are all silicon. So that being said, so we said that this is the intrinsic silicon. It's an insulator, and if I use thermal generation, I will move electrons, and I will have holes, and then the next atom will also release its electron. They recombine with a hole here, and the electrons will all be, you know, so all the electrons and holes will be recombining. So it's an insulator. But did I have the ability by thermal generation to break the covalent bonds? I did, right? So it is possible to create or break the covalent bonds in silicon using thermal generation. That's something we want to agree to. But in intrinsic silicon, it doesn't buy me too much, right? So, and that's what they're talking about here. So at room temperature, some of the covalent bonds are broken by thermal generation. So we said at 0 Kelvin, it looks like this. The structure is similar like this. The covalent bonds are intact, they're in place. You start raising the temperature, okay, put it at room temperature, and the covalent bonds, okay, they will start to break, the electrons start moving, but it finds a hole, it recombines. The other electrons start
So it's
moving,
not
it
as-
finds a hole, it recombines.
It's like, it's not as conductive as like copper, but it's not as insulated as
No, there's no conduction, because if you take a cross section, you know, okay, this electron moved here, the other one moved the other side, and then this one recombined and this one recombined. So as a whole, it's an insulator. There is charge movement inside, but if you connect an external circuit,
It's gonna give you.
no current will flow, because the concentration of free electrons and concentration of free holes at any period of time in intrinsic silicon is the same, which leads us to this equation here. So N is the concentration of electrons, and P is the concentration of holes, and Ni is the concentration of electrons in intrinsic silicon. Okay, so because later we will put subscripts here, you know, N or NP, and we will see what that means. But in general, in intrinsic silicon, the concentration of electrons and the concentration of holes are equal, and they are equal to, fine, this is the concentration of holes, electrons in intrinsic silicon. So they're all equal, right? And again, these equations, by the way, I don't think the homework covers. I don't think we need to know a lot of the equations here. It's just a theoretical part of this material. Yeah. Some of these equations, if you're using the homework, fine. But if not, I don't think they're used in the homework. Yeah. So I think we just cover the theoretical side. I just want you to understand. So we're leading towards understanding how the diode works today. That's our objective today, to understand how the diode works. And then we start next class with, okay, diode circuits. So today we're just talking about, you know, how this stuff works. Yeah. So these are all equal. Do we agree? Is everybody on the same page now? And these are concentrations of holes and electrons in intrinsic silicon. We said that this intrinsic silicon you can still excite the extrinsic silicon, or the electrons and holes in the intrinsic, they will still be moving among themselves, and that will be done using a thermal generation process, right? So this will talk, yeah. So the concentration of electrons in intrinsic silicon, we will find that it's directly proportional to temperature. and some other stuff, okay? So temperature, but temperature appears here, and temperature also appears here. So temperature appears in the exponential, and temperature appears, as a constant here that is directly proportional to the intrinsic silicon concentration, right? So this is an important thing to understand. What are the rest of the variables? So B is just a material dependent parameter, and it's equal to a certain value for silicon. Fine, I don't care what this is here. E is it's called the band gap energy. Notice that it is appearing up here. So it's gonna affect how this exponential function. The exponential function looks like e to the minus x will look something like this, right? So e to the 0 is 1, and then e to the minus x will look like this. So we have e to the minus eg, blah, 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 a few things over temperature, right? So temperature and this band gap energy really affect what the Ni is proportional to some constant multiplied by this exponential, right? So whatever we're multiplying by the constant is dependent on temperature. So I'm multiplying it by this exponential function. This exponential function highly depends on the band gap energy and the temperature as well, right? So do we want high band gap energy? If we have high band gap energy, the concentration goes low. Low band gap energy versus low band gap energy, it goes a little higher, of course, for the same temperature, right? So it's something to consider. So silicon probably has an ideal band gap energy to allow the concentrations to do whatever we want them to do. So let's see what we want them to do. Do we want the silicon to behave in such a fashion that when I increase temperature, I have electrons becoming free? Do you want the process of current flow to be only temperature dependent? No. I do not want the process of current flow to be only temperature dependent. So since that is the case, I do not really like this. I mean, this is, for me, having the same concentration of holes, same concentration of electrons as in intrinsic silicon means that there's no net current flow. And only net current flow will occur, and these electrons can only become free if I increase the temperature. It's not something I can control. I don't have an interest in that. So what do? We do what is called, we add impurities to the silicon so that we can control the current flow somehow, right? So if you go back here, if I introduce an atom here that has, instead of 4 valence electrons in its outer shell, I introduce an atom here that has 5 valence electrons in its outer shell. What's going to happen? Yeah, this atom will fill, again, it will fill this space in the material that I've designed it to fill, right? It would fill one of the places of the silicon atoms, right? It will go into this configuration, sit there, and because this is a solid material, it will be building these, and it has 5 valence electrons in its outer shell, meaning it has one more electron than the silicon atoms around it, right? So it will be able to share 4 electrons with neighboring silicon atoms, right? It will be able to share the 4 electrons. Everybody else has 4 valence electrons, right? If everybody else has 4 valence electrons, they want to be sharing 4 valence electrons with their next door neighbors, right? So this new atom that we've introduced here, for example, phosphorus. Phosphorus is one material, phosphorus. So phosphorus is one material that has a valence of 5, meaning has 5 electrons in its outer shell. Everybody around you wants to share 1 electron so that they fill their outer shells. So now everybody else has their outer shells filled. You have an extra electron that you're not able to find somebody to share with. So what's going to happen to that electron? It will just become a free electron.
And that's what's going to cause the current to...
This is something that can cause current to flow, right? And this is something that causes current to flow in a controlled fashion. This is an electron that moved. So you created a free electron, and what happened to where it was? It's like Can you imagine like a donut here thing, and then the electron is sitting on this? So this is like my electron. And this is like the electron, and this is the hole. So you left like a hole behind. Right? So it's like the electron becomes free. The electron became free, it left a hole behind.
Something, another electron.
But there's nothing. In this specific picture, nothing else can come back. Nothing else can fill it, right? But if I add many of those, let's say I add another one. If I add another one, then what can happen? Then the electron that I pushed out can maybe come back and fill this hole that is here, and this electron can go fill the hole in the other one,
So it's not,
right?
it's
But
not-
only for these two. Exactly, so it's still an insulator.
So what's the use?
I will come to the use. That's good that you realize. That's good. So also, if I even start introducing these impurities, then I'm still not conducting current as such, right? I have a higher concentration of free electrons than holes, right? I have a higher concentration of free electrons in this case, because again, you don't have any free charges anymore, free holes. You really have a bound positive charge to the atom. It's a bound positive charge. Only the electron was able to becomes a free electron. So you have, if I add more of these atoms, then I will have a higher concentration of these free electrons, right? And the concentration of free electrons in this case, fine, they can recombine. Right? If you have the even number of these impurities, they will recombine. I understand, but which is why when we add these materials such as phosphorus with a valence of 5, for example, we call this material N-type material. So it's doped with an impurity. This impurity happens to be phosphorus. This phosphorus has a valence of 5. It's called an N-type material. N-type. Why is it called an N-type material? Because I have these free electrons that I can figure out. Maybe I can figure out something to do with them. Okay, as by itself, an N-type material by itself is also non-conducting. It will not conduct current. If you connect a material, circuit, external circuit around the N-type material, it will also not conduct, because if you have a certain number of these dopant atoms, then the free electron can recombine. Okay. However, if it becomes free, right? Is it becoming free? When it becomes free, is it becoming free because of temperature? No, it's becoming free because I added an impurity, right? So as soon as it becomes free, maybe I can do something about that. Maybe I can push it with an electric field, right? So that's something we will think of how to think of doing next. But as it is also an N-type material, if I add dopants, fine, I have these free electrons that can recombine. They can recombine, but the concentration of free electrons that exists, is it equal to the concentration of holes that exist? Before, in intrinsic silicon, the number of electrons that existed was equal to the number of holes. So the concentration of P was equal to the concentration of N, was equal to the intrinsic silicon electron concentration. And that was affected by temperature, right? Now, I have an N-type material. In N-type material, I added a dopant. So this dopant caused the free electron to exist. So what is the concentration of electrons in an N-type material equal to? As soon as I add one atom of the dopant, I get one free electron. As soon as I add a second atom, I will get another free electron.
So it's just proportional to each other. So
Exactly. So it's proportional to the dopant concentration. I think that's what they call it, dopant concentration. Yeah, that's the dopant concentration. So the amount of free electron, the electron concentration, the free electron concentration in N-type silicon is equal to the concentration of the dopant atoms. Dopant means impurity. If in sports it means you're taking drugs to accelerate your abilities, blah blah blah, right? In electronics, it means you just added
Drugs.
taking drugs. So you have silicon on drugs, yeah. So this is being recorded. It's not good, yeah. Oh yes, by the way, there was one example. You know the example on with integrator. The example in integrator in chapter 2. I drew it such that I integrate a DC, right? And then the pulse, the input was a square wave, a pulse. As soon as the pulse went down to 0, I said that this goes down to 0, right? But remember, when we integrate, we always have to consider the initial condition. So the initial condition for the next, the input was initially a constant. What's the integration of a constant? Integration of a constant. A ramp. Fine, it happens to be a negative ramp because V output is equal to negative VC, right? So it was a negative ramp because the input voltage was a constant, right, here. And then the input voltage became 0. What's the integration of 0? It's 0, but I have the initial condition, right? And remember, integration of anything, you have to add the initial condition. The initial condition for this new voltage 0, for this new integration is what? Is what I had before at the output. So the output will look like this. It will not fall to 0. Right? This is my initial condition for, I'm not adding, integration is the area under the curve. So this was the area under this curve. It started a very small area, right? And then you kept adding area. That's why it's a ramp. And then, this is your initial condition for your new condition, which is integration of 0. Integration of 0 is 0, but plus your initial condition, right? When you solve, it's plus the initial condition you had before. So your initial condition was now this, the final value of the ramp after 1 millisecond, right? So please note that, because the problem is that everything is recorded, right? So look at it. If you still have problems, we can do it. We can do it in my office or something. Okay, let me delete this and get back to dopants. So, no. Okay, we have to continue. So anyway, do we all agree now that the concentration of the free electrons is equal to the concentration of I put a dopant, I got a free electron. Fine, this free electron can recombine. I understand that. But I know that the concentration of free electrons is equal to the number of atoms of impurities I added. Same with p-type material. But what do you think we're going to do in p-type material? So in n-type material, we put an atom with an extra valence electron that allowed the electron to just become a free electron, leaving behind a bound positive charge or hole.
An atom with less.
P-type material is something. Okay, so what is n-type material? N-type material is material where the concentration of electrons is controlled by the dopant atoms.
So n-type has free electrons.
Again, n-type by itself will have a free electron, but then this free electron will recombine again with the hole. It's going to fall into the hole that was created by the other dopant atom. But so by itself, it's an insulator also.
As soon as we
But-
have the free electron, we can do something.
Yeah, when you have the free electron, you can do stuff with it. That's fine. But here I'm talking about concentration first, okay? Because why? Okay, just so that you can be excited. So if I'm able to increase the concentration of something somewhere, right? And then I, put this stuff in a place where there is the concentration of this same material is not the same. So let's say you have a spray can. If you have a spray can, right? The stuff is concentrated in the spray can. When you spray it, what happens to it? It's dispersed. It diffuses into the atmosphere. So same thing happens. Okay, so that's why. So we're going to build n-type material with a high concentration of electrons that we can control. Then we can introduce it to the p guys. When you introduce it to the p guys, there's no n here, so they will be attracted from high concentration to low concentration, causing current to flow. Right. So this is the main mechanism of current flow. One of the main mechanisms of current flow, or the most important for us here for this for the diode.
Flow depending on the concentration.
Yes. Yeah. Because these things will, they will find. Okay, you have a lot of electrons, free electrons. If you imagine you fill instead of these 9 being the ones around it being silicon, you put more than half of them being the impurity. What's going to happen? Then you have a huge concentration of free electrons available in a certain place. These free electrons available in a certain place see holes far away, lots of holes far away, right? Lots of positive charge far away. They will be attracted to that. A lot of them will be attracted to that positive charge. Some of them will recombine locally. A lot of them will diffuse and be attracted to this positive charge, right? So that's what's going to cause current to flow. So obviously, this is N-type material. So P-type material is what? Come on.
It's
It's
gonna have
positive,
less.
so it's gonna have 3.
Exactly. It will have a lower number of electrons in its valence shell, so it's going to attract atoms, basically. It will attract an electron from a neighboring atom, so it's going to attract an electron from silicon. This electron will be bound to this new atom, and I will be left with a free hole.
And that's gonna attract another. Is that gonna attract another one?
Yeah, of course. If you leave P material by itself, it's also an insulator, and they keep reattracting and combining. It's called recombination. It's called recombining. So it's called a recombination process. So, but the benefit I got was what? Is that I got a concentration of holes in P-type material equal to the number of acceptor atoms. So this atom will accept an electron, right? So now I have, concentration of holes in P-type material that I can control. That the concentration I understand, I know. And again, our objective is to be able to create material with a high concentration of something, and introduce it to something with a lower, a place that has lower concentration of that material, so it will flow to it, it will diffuse to it, right? That's the whole objective here. But does this material only have, free electrons, or are there holes that find this free electron is, it's a free electron, but what did it leave behind? A bound hole, right? So there are also so in an N-type material, there's a concentration of, electrons controlled by the number of dopant atoms, right? How about the concentration of holes in the N-type material? Yeah, how about the concentration of holes in the N-type material? Do I know, can I control its concentration?
Yes.
How?
Because you will be putting like the new impurities. So you know the
Yeah, you got a concentration of free electrons. As soon as you put one impurity, you got a free electron. You got a free electron. No, you did not get one hole. Where did you?
one free electron.
One hole in the impurity. You did not get. This is a bound charge. It's not from the silicon. It's from the new impurity. But I'm talking about from the silicon itself. So you did not really get that. You did not get any free holes in that case. But you still have. I mean, you have holes in electrons. Again, each one of these electrons around the silicon atom, if it leaves, it will leave behind a hole in the silicon, right? So how do I make this electron leave? Sorry, yeah, how do I make this electron leave? Leave. I want it to leave so I can get a free hole. Exactly. So now if I heat this material, so first I put this dopant. When I put the dopant, I got free electrons from my dopant atom. So now I know that the concentration of free electrons is equal to the number of dopant atoms, right? In the N-type material. How about the concentration of holes in the N-type material? The same material, concentration of holes. For me to get a hole in the silicon, I need to have one of the silicon covalent bonds broken. And the way to do that is by temperature, because I don't have any other mechanism to do that here. So if I bring it to room temperature or higher, then I can break these covalent bonds, and fine, one of these electrons will leave. Fine, you recombine with another one, that's fine, but it will leave behind a hole. So the concentration of holes in that case is controlled by temperature, right? So the concentration of holes in this case, so the concentration of holes in N-type material is controlled by temperature, right? Like what? Like the concentration of holes and electrons in intrinsic silicon. Okay, so remember, intrinsic silicon, I had holes and electrons concentrations that were controlled by temperature. And they were all equal to each other. P is equal to N equal to Ni. And Ni was equal to blah, 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 something with exponential and temperature. band gap energy, and so it's something dependent on the material and temperature. So this is intrinsic silicon. N-type material. N-type material, I have electron concentration controlled by the dopant atoms. Hole concentration that I have no control over. It's controlled also by temperature, which means it's like the hole concentration in intrinsic silicon, right? So we happen in intrinsic silicon. I also skipped one equation. So because P equals N equals Ni in intrinsic silicon, P times N is equal Ni squared. Okay. Right? We agree with this? Because they're equal to each other, and I multiply them by each other, it's equal to Ni squared. Okay? So this actually happens to hold in silicon in general, whether it's doped or not. So now let's see how it applies to N-type material. We said that in N-type material, N is controlled by the concentration of dopant. How about P? P is proportional to temperature. So, and here if I want to solve for P, P is Ni squared over N. So this is intrinsic silicon. How about in N-type material? P, the concentration of holes in N-type material is going to be Ni squared over Nd, because Nd is the concentration of electrons in N-type material. Okay? No? Too much information? Yeah, Ni squared over Nd. So why squared? Because it comes from here. Remember, P times, huh? Why what? Because we said that P times N equals Ni squared. This is the relationship we understand how to find that from intrinsic silicon. It happens to be that this relationship will always hold for silicon. But for N-type silicon, we know that Nn, the concentration of electrons in N-type silicon, is controlled by the number of dopant atoms. So if we apply this, what do we get? So P times Nd is equal to Ni squared. Still, this equation still applies, which means that P is equal to Ni squared over Nd. Ni squared is the concentration of electrons in intrinsic silicon, which is controlled by temperature, right? Which means that the concentration of holes, it satisfies our explanation, right? It means that the concentration of holes in N-type material is controlled by temperature, and the concentration of electrons in N-type material is controlled by the number of dopant atoms that you add. Okay? And if I add more of these dopant atoms, I create, this N-type material there. So how about P-type material? I won't spend too much time on P-type material because it's exactly the opposite, right? So we have an atom impurity that we add that accepts an electron. Accepts an electron, this electron becomes a bound charge. We have a free hole in that case, right, in the silicon, right? So in that case, we said that the concentration of holes in the P-type material will be controlled by the number of acceptor atoms I add. This equation still holds, so P times N in Np is equal to Ni squared, which means that the concentration of electrons in P-type material is equal to Ni squared over capital Na. Right? So the concentration of electrons in P-type material is controlled by temperature. The hole is controlled by concentration. So do we see? So now I can create a P-type material, and I can also create an N-type material. Let's see what we will do. Obviously, we will not be able to get to that point, but come on, I have another minute, man. Huh? No, by themselves, they're insulators. No, I'm just kidding. If you want to leave, leave. Yeah. So, but just by themselves like that, nothing will happen. But if you bring them close to each other, then you have a high concentration of holes somewhere.
I know, but
Yeah.
in air,
In air, Na is the concentration of acceptor atoms. So we put an acceptor atom like boron. Boron is an atom with valence of 3. So as soon as you put that, an electron will be pulled from the silicon. This will be bound to that atom, leaving a free hole behind from the silicon, right? So so now we've created p-type material and we've created n-type material. But we said that none of this, there's no net current flow, because you put two donors, 2 electrons will flow, will become free. They will just change with each other, or even if the temperature is a bit high, everybody will keep changing with each other. But I don't have any net motion of current yet. So how do you create net motion of current? Fine. There are 2 mechanisms called drift and diffusion. So these are the 2 mechanisms of charge flow, hence current flow. I will stop here. I was hoping I think our discussion at the beginning sort of pulled us back, but